strong acids and strong bases completely dissociate in water. So if I take a mole of strong acid, HCl, hydrochloric acid, and I put it in water, I get a mole of H3O plus and Cl minus. That complete dissociation is what characterizes it as a strong acid. Some acids and bases don't completely dissociate, and we call those weak acids or weak bases. Let's look at some of those. Here's acetic acid, HAC, reacting with water. Now, AC minus, I've abbreviated. The acetate ion is actually H3CCOO minus. Just AC minus here for convenience. So the acetate ion formed by HAC, acetic acid, reacting with water to form H3O plus and AC minus. In this case, water acts as the base. It accepts the proton from HAC, forms H3O plus. We can write an equilibrium constant for this reaction, Ka, 1.8 times 10 to the minus 5. Now, that's much less than 1. And you know a K less than 1 means this reaction at equilibrium favors the reactants. So there's another difference between the strong acid and the weak acid. At equilibrium, the strong acid favors the products, complete dissociation. The weak acid favors the reactants. You can look at it in terms of free energy. Since this K is less than 1, the standard state free energy difference is positive. So this is a non-spontaneous reaction. Again, non-spontaneous does not mean it doesn't go at all. It just means at equilibrium, the reactants are favored. For a strong acid, by contrast, the standard state free energy difference is negative. That's a spontaneous reaction. And at equilibrium, the products are favored for a strong acid. Now, we can take minus log of the equilibrium constant Ka and form a pKa, just like we took minus log of the H3O plus to get pH. So this is a pKa of 4.7, and the smaller the pKa, the larger the Ka. So a small pKa means a relatively stronger acid. The smaller the pKa, the stronger the acid. Let's look at the conjugate base. Here's the conjugate base acetate ion reacting with water. The conjugate base reaction, AC minus, acting like a base, accepting a proton from water, is what we're looking at here. Now, AC minus is the conjugate base of acetic acid, but notice the conjugate base reaction is not just the reverse of the acid reaction. The reverse of the acid reaction would be AC minus reacting with H3O plus. Here's AC minus reacting with H2O. So when I write the equilibrium constant for this, I'm writing a reaction with H2O and AC minus. I can get a Kb for that, 10 to the minus 10, and a pKb, 9.3. Again, you'll notice this is a small number. This is a weak base. This favors the reactants. You should also notice that Kas and Kbs, even though they're not reversed, that is, Ka isn't 1 over Kb, they are correlated. The larger the acid dissociation constant, the smaller the base dissociation constant. And that should be obvious because the stronger the acid, the more this equilibrium lies towards AC minus in solution. So AC minus should be favored in solution. That means this equilibrium constant must be small. So that's how Ka, pKa, Kb, and pKb, the acid and base dissociation constants, are related for weak acids and weak bases.